Hi everyone, you're looking at a quick update, which is the removal of 4 of the poles on the reluctance motor rotor, and that actually has been ground off by my just regular hand angle grinder, and then just filed down by hand one at a time, and I've made them perfectly equal, and you can see that there should be actually no need to rebalance the motor here. Everything is should be perfectly fine. I've checked it roughly as well, and it seems to be good. I've also redone my optical reflector, and actually I have a tape there, and they are actually at the width of the pulse width, the on time that I need. And I'm going to just go straight direct without the circuit to adjust pulse width, just to verify the difference. And so I'm going to pop that guy in, and we should see it running. Okay, so here is the motor now working with all 3 phases perfectly adjusted in timing and all of that. And I am using the full circuit here to have control over the position and pulse width of each phase. So there are 3 phases. So like this potentiometer here controls the timing, and then this one the pulse width, and timing, pulse width, timing, pulse width. So there's the 3 phases, and it's all perfectly set now. I'll give you a scope shot. Here what I can do, I made this little box here so that you don't get disturbed by the light of the room. And there you have the scope data, and you see the yellow and light blue and purple at the bottom there, kind of in a step matter. I've just separated them so you can see each phase operating. So I have a voltage probe on each one of those, being the yellow, light blue, and purple. And on the top and the center across there is basically the current sensing resistor. So that is the current being going in each phase there. So as you can see, the current is perfectly identical because it's all been perfectly tuned for that. So now what I'll do is I'll zoom in, so I'll give you a little closer data. And there you have the data there. So on the top there you have the voltage, RMS voltage. Well, we really need to actually have a lot more samples to give you an accurate reading. So that would probably reflect more the voltage RMS. But there is a lot of switching noise. As you can see, there's little spikes there that go up and down. What I'll do is I'll just do a single shot there, get a frozen frame here, see if we can get some accurate data here. Okay, that should be able to give us some more or less accurate data there. There's no peaks going off the page. Anyways, that's what it looks like. I'll zoom in there just so that you can look at pretty well just one single phase at a time here. I'll freeze the frame, and that is, there you go, just one single phase there. And I'll give you more here. I'll give you all the 3 phases here. I'll do a single shot. So there you go, you have a view of all the 3 phases there. Sorry, just have noticed the camera there is a little off on the edge there of the box. So that is the view of the scope. And this is all being powered by batteries. So basically I have 2 batteries in series, 2 12-volt, these are 5 amp hour batteries in series, There's one phase here, there's a second phase there, and there's another phase there. I had to do that because I needed isolation between each phase, and to build isolation in a circuit would be really complex. And what was happening basically, if I don't have isolation and I'm powering all from one single source, is the flyback event, which is when the coil shut off, that energy that comes back out and was collected in coils would actually go back in the input of the next phase. So that was an issue, so that's why I had to create this isolation. So each battery bank is completely isolated, and then I have my MOSFETs here for each phase, and there are my probes, so yellow, light blue, and purple. And there is my current sensing resistor, which is 0.01 ohm 1% resistor, and that's a bunch of basically 0.1 ohms together, so it gives you 0.01 ohms, 1% accuracy, and it's more accurate basically when you have 10 of them bunched together, so it's very good precision resistor. So now basically the flyback of the motor is going to these three batteries. Again, each battery is somewhat isolated as well, and these were down to around 12 volts, 12.12 when I started the device, the motor, and now they're above 13 volts, so they're pretty well fully charged. And the whole motor here has been operating at, I'll give you a tachometer reading here. So 2,000, sorry about that, pretty close to 5,000 RPM, 2,495. And basically 6 hours ago I started it, and it was 2,470. And it hasn't dropped, actually it has increased, probably because the bearings get a little looser. And basically these are the batteries here. So I wrote basically the red phase, the yellow phase, and the black phase. Those are my colors of my wires here. So yellow, black, and red, which is brown, but I call that black. And anyway, so we had about 25.93 volts across, so pretty well around 25.9 when we started. And these batteries are still at about 25 volts across them, and they will recover once I stop this. I'm going to stop this after the video. I'm not making any claims here. This is just showing you that, you know, it's been operating, you know, it's pretty efficient turning at that RPM. And I did the math on it. I have this meter here hooked up to one phase. I hooked that up so that you get an idea of how many watts is going in. So it says 24.7 volts here. That's because there's a low voltage drop on that resistor. And then these are the milliamps, so 127 milliamps at 24.7 volts. Comes to about 3 watts. So basically you're looking at 9 watts. This has been operating at 9 watts about for the past 6 hours now with these 2 series 5 amp hour batteries. And now these batteries here, like I said, are pretty well fully charged. One of them actually is at 14 something. I can turn on the meter here, give you a reading. Just a little difficult to do this all by one hand there. Give it a try. See, that one's at 14.63. That one's probably pretty well fully charged. That one's at 13.12. And this one here is pretty well 13 volts. So that is just to show you that this is operating very smoothly and very well. And the next test now will be basically doing a load test on the motor itself to find out, so putting a mechanical generator basically on the shaft and measuring the output in watts that we are getting, and seeing the difference there. Now the other interesting thing is, because of the way the circuit is and the motor being fairly efficient, is if I put a load on here, if I load down the shaft, you're not going to see any increase in power here. So what I'm going to do right now, I'm going to give you a view here of the meters. Sorry about the light reflection there. Okay, there you go. So I'm loading down the shaft now. You should be quite easily hearing the motor decelerating. And we're going to take a tachometer reading. So you hardly saw any difference there. We'll take a tachometer reading. So there you see it recovering its RPM. And there you go, pretty well at where it was. And then we're back there again. So that's an interesting feature. Basically, you know, you're not getting any extra input basically for the shaft being put under load. That should work very nicely as well when you put the generator on. Basically what you're getting out of the generator is not reflected back to the input. So that will be good. What I'll do now is I'll just zoom in here, and I'll do the same. Going to hold the shaft, put a load on the shaft, the motor here, so you can see the dynamics. Letting it go. So basically no disturbance on the current, and that is a good sign. So we're definitely on a right direction with this. And like I say, next video is going to be just load tests. Thanks for watching. Bye now. Oh yeah, I almost forgot. Basically I think I'm going to just shut this thing off here. This here is the supply, the battery here for the logic for controlling your switching and all that. I have an identical motor here as this motor, but this one here I got the original circuit that came with this motor, and this is what it would use basically. And I'm going to plug it in, and we're going to just look at one of those kilowatt meters here. So there you go. Let me just push that in there. So that motor is consuming basically 16, a little over 16 watt, close to 17 watts right there. And we can see, you know, basically we're on the grid here, 122 volts on the grid, and I guess that's the power factor. That's the frequency, 60 hertz. That is the volt amps, and that there is the watts. So 16.6. It probably will drop down to about 16 watts once it's warmed up, but it's turning at a very low speed. And I'm just going to load the shaft just slightly here, and you're going to see there's a shaft load. Look how fast it jumps up, 40 watts. So I'm loading it at about the same rate as I was loading this motor here when I did that. And here it's the opposite. It just consumes power. And the other interesting thing is, well, this circuit, I don't have what's needed to activate it to go to higher speeds, because I need the other part that goes in this front end here. Unfortunately, I didn't get that with it, and it's pretty expensive. I'm going to see if I can try to find something, and if anybody knows what the communication protocol is here to get this. This is the driving chip here for this whole thing. If you know the communication protocol to put in these 3 pins here, I believe, to get this controller here to tell this thing to go higher up in RPM, that would be great. Anyways, I'm going to see what I can do. Now look at this here. It's just idling now, and it's only at 730 RPM basically. So at 16 watts, let's call it 16 watts, you're getting 730 RPMs. So that's a point there, 730.6, you know. So that's all the RPM. You can see it's slow. Focus. Okay, so anyways, thought that was kind of interesting, and seeing that it's a real hog basically in, you know, this kind of configuration. So I think we're in the right direction here with this. Thanks for your interest. Bye now.